Sure.
Okay, let me introduce our next speaker, Hwan from Korea Advanced Institute of Science and Technology. I am very excited. I have known Professor Yu for almost 15 years now. Time flies, all right? And Professor Yu has graduated from KAIST and then moved for his postdoc to the University of Washington in Seattle, and then where he was doing passivity-based teleoperation and with time delay, and then also has worked in the DLR, which is the German Aerospace Agency, where he also continued his work on teleoperation. And so Professor Ryu is a world expert in this area. I believe one of the most active proponents of haptics and one of the most active members of the IEEE Haptic Society. Is that correct? The chair of Asia Haptics Conference, and it's just, I can go on with listing your regalia, but we don't have enough time, and I'd rather you talk. So anyway, I'm very excited and very thankful that you accepted our invitation, and please go ahead with your talk.
Okay. Thank you, Igor. Thank you, Igor, for such a nice introduction, and I'm really happy and honored to give a keynote speech in NIR conference. And especially, I would like to thank Professor Igor Gafanov for inviting me as a keynote speaker and all the organizing committee to organizing such a nice and wonderful conference. Today, I would like to talk about some of the control method for assuring safe physical human-robot interaction that I have been working on the last 20 years. Okay, so I'll briefly summarize what I have done. Okay. And before I move on, I would like to briefly introduce some of the research area in IRIS lab that I'm leading as a PI. So basically our lab doing 4 different research topics. The first one is haptics and telerobotics, which I'm going to talk about today. And the second topic is muscle-like soft actuator, twisted string actuator, and exoskeleton or exosuit based on this actuator. We recently started up a company based on this topic. And the third topic is vine robot, which is a plant-like growing robot. We have started collaborative research with Stanford on this topic. And the last topic is autonomous vehicle, which is more like a hobby project with me and my students. So we've been developing autonomous vehicle mainly for participating autonomous vehicle competition organized by Hyundai Motors. And luckily, we won in the competition last year. Okay, it's like we are doing 4 totally different research topics, but actually our theme is human and robot interactive system. So we are developing some interactive robotic technology or interactive robotic control schemes, human-robot interaction. Okay, then let's get back to the main topic. I've been working on haptic interface and haptic system for many years. And what is haptic interface? I guess all of you already know what is haptic interface. So haptic interface is a mechatronic system to allow human to feel and physically manipulate virtual or remote environment. In a sense that haptic interface is closely or physically interacting with human. So safety is one of the critical factors. So safety is really important. And if you look at the haptic interface, there are 2 different types of haptic interfaces, impedance type and admittance type. Not only haptic interface, but also all the general robotic system, which physically interacting with human, you can categorize those robotic system into 2 types, impedance type and admittance type. And what is impedance type? Impedance type usually measure position and provide a force command, and backdrivable and lightweight. So good for low impedance display, but it's limited to display high impedance. On the other hand, admittance type haptic interface measure force and provide position command. So usually non-backdrivable and heavyweight. So it is good for high impedance display, but it's quite limited for low impedance display on the other hand. And let's talk about impedance type first, okay? If you have a experience on impedance type haptic display like a phantom, then you may try to increase the stiffness as high as possible. But if you increase the stiffness above 2 or 3 kilonewton per meter, then you may hear very strange sound like this. I hope you can hear the sound. Okay, I will stop it. Did you hear sound? Okay, hopefully yes.
Yes, we did.
Okay. Yeah, all right, good, great. And that's the kind of unstable behavior and instability. And for telerobotic system as well, if you try to increase the virtual coupling between master and slave, okay, we suppose not using master and slave, haptic interface and the remote robot, then let's see. Okay, that's enough. So such a highly unstable behavior. Okay, then how to stabilize those unstable behavior? So usually people try to add damping, either physical damping or virtual damping, but that actually shift the impedance range, not increase the impedance range. Also, limit or adjust the stiffness. That's basically lower down the controller gain with virtual coupling or energy bounding like a method. But this one also, it compromises the impedance range. So basically we can stabilize the system, but we need to sacrifice and compromise the performance. So there's always trade-off in stability and performance in whatever haptic or robotic manipulator control. So if you want to increase stability margin, then you have to sacrifice performance. And if you want to increase the performance, you have to sacrifice the stability margin, okay, vice versa. And about 20 years ago, I have proposed the time domain passivity approach, one typical control approach. And this control approach known as one of the least conservative control approach in this kind, because it minimally modified the original optimized controller structure or controller gain. So it's known as one of the least conservative control approach. It has two components, passivity observer, which can measure energy flow in real time, and passivity controller, which is kind of adaptive energy dissipation element whenever it is necessary. And let's talk about what is passivity. Passivity is based on the conservation of energy. As you all know, energy supplied by the network can never exceed the energy which has been fed to it. So this is the mathematical definition of passivity. So let's say there is one port network system or one whatever physical system. Let's say this is my key, my car, okay? So if you push the system and the resulting velocity is same as the force direction, that means you provide energy to the system. But if you push the system, but the resulting velocity is opposite to your force direction, that means the system gives back energy to you, okay? Energy comes out of the system. So if you integrate this power conjugate pair, product, force and velocity, power, for all the time to get, considering initial energy storage, if this value stay positive for all the time, that means system is passive. So that's a mathematical definition and the physical meaning of passivity. So let's a simple example with a spring. So there's a spring. So if you press the spring, then you give energy to the spring and energy is accumulated inside of spring. At some point you let it go, then spring start to actually give out energy back to you, but never greater than what you give to the system. So spring is passive. But if spring is initially deformed, then after that you start to press, then energy actually comes into the system, spring, from this point. But at some point, if you let it go, then energy comes out of the system and bigger than what you give. But still the spring is passive because it never go down below zero. So that's the mathematical and physical meaning of passivity. Then why passivity? We care about passivity because passivity has a very fascinating property. Sufficient conditions for stability. So if the stability anymore, and it can draw global conclusion from individual part. So if individual part are passive, then overall part is passive. So you can individually passivate the system. And we can, consider nonlinear or whatever nonlinear system by simply considering input and output signal. So it's very fascinating property. Passivity has many fascinating properties. So we propose passivity observer and passivity controller. Passivity observer is an energy monitoring component. This is, as I mentioned, mathematical definition of passivity, but it's quite challenging and difficult to satisfy this mathematical condition in real time because this is very simple but nonlinear. What other people did was converting this into frequency domain and design some controller in frequency domain and convert it back to time domain. So that actually end up having fixed controller gain considering worst case. But what I proposed is extremely simple, too simple actually. What if we integrate this in real time based on the monitored signal? And if this value stay positive all the time, then system is passive. We don't need to worry about the passivity. But at some point, this value goes down below 0, then system is active. But the good thing is, since we are monitoring this in real time, every sampling time, so we know how much energy is produced in real time from the system. Since we know how much energy is produced in real time, so we can put adaptive damping element or adaptive dissipation element, depends on causality. So impedance causality, we can put series type passivity controller, and admittance type causality, we can put parallel type passivity controller, which basically means modifying force based on velocity and modifying velocity based on force. And the beauty of passivity controller is that it can very easily implement it to existing control architecture. So by adding several lines of C code, you can implement passivity controller. So this is the main core part of the passivity controller. Only 3 or 4 lines of C code is enough. Okay. So let's take a very simple example with a virtual wall with spring and damper. So there is a virtual spring and damper in parallel virtual wall, and which is equivalent to a register capacitor serially connected electric circuit. And the physical meaning of passivity controller is adaptive register or adaptive damper, which appear and adaptively change whenever it is necessary. Okay. So I push and release with this velocity profile of the virtual wall. Then much energy first comes into the virtual wall, and a little less amount of energy comes out of the virtual wall. And that difference is actually dissipated by the damping of the virtual wall. But when I intentionally change the virtual damping to negative value, which is not physically feasible, but I just want to make the system intentionally active, then bigger amount of energy comes out of the system than I gave. So it's basically active, become active. And I turn on passivity controller to dissipate this. Then when this energy is about to cross the 0 line, then passivity controller adaptively dissipate all the produced energy in real time. So if you look outside of the system just looks like passive. Okay, that's very simple. And the first, the passivity controller is first implemented to Excalibur haptics interface at University of Washington when I was a postdoc over there. This haptic interface can display 200 Newton force maximum each axis, and it is interacting with virtual Lego airplane. And the issue was, what was the maximum allowable stiffness that we can display? One of the former PhD student over there, Rick Adams, he proposed the virtual coupling idea to stabilize haptic interaction. And the maximum stiffness that virtual coupling can stabilize the system was 70 kilonewton per meter. But I increased this value to 90 kilonewton per meter, which is very high, extremely high. And as you can see, this contact was quite unstable. But after I turn on and implement passivity controller, we were able to achieve stable interaction and stable contact while maintaining the high same virtual stiffness, 90 kilonewton per meter. Okay. That was the first implementation. And I extended this idea to multi-port case. in order to implement similar idea to telerobotic system in other control system. Then the issue was, okay, then one port case, it was straightforward, but for multi-port case, okay, where to put the passivity controller and how to monitor energy, what type of passivity controller, how to activate this, those are all questions. So I'm not going to explain this in detail, but you can see the paper over there. And I developed master slave telerobotic system, tuned off with force and torque sensor at the tip. So as you can see, if I approach slow velocity, there was no stability issue. But if I made a contact with normal velocity or high enough velocity, then system suddenly goes unstable. And with passivity controller, we were able to make stable contact and stable interaction. The off surface following example, at the beginning it seems like stable, but it goes unstable as you actually move. But passivity controller were able to stabilize this interaction as well. Okay. And after that, I was invited to German Aerospace Research Center, DLR, because they want to implement this control algorithm to their ground space bilateral teleoperation system. And in order to implement this idea, we need to consider time delay. Okay, that was a critical issue. And if you look at the control architecture of telerobotic system that I have implemented in previous video clip, this is a teleoperator and telerobotic system. And if I magnify the teleoperator part only, there is master, there is slave, and bilateral controller. And what I did was extremely simple. Just took power conjugate pair from both bilateral controller and integrate this and measure energy, estimate energy. And whenever there is output energy, which possibly makes system active and unstable, then I put adaptive damping to dissipate this in real time. That's the architecture, basically, what I did. But when there is time delay, it was impossible to measure energy flow at the same sampling time because there was time delay between master and slave. So it was very difficult. So together with DLL researcher Jordi Artigas over there, we have actually extended time domain passivity idea considering time delay. So the idea is also very simple. So by looking at the power conjugate pair, we can separate input and output energy. So by simply monitoring input energy on one side and also output energy on the other side, and send input energy to the output side, energy side, and compare output energy and input energy, transfer the input energy. And when the output energy is about to be greater than the input energy, then we put adaptive damping and dissipate this. So that's the basic idea. And that idea has been implemented to phantom teleoperation in our lab. And this is not my voluntary motion. I was not able to actually make a stable contact. So it became crazy, even 100 millisecond time delay. But after TDPA implemented, as you can see, the contact was stable, and I was able to manage stable contact, and the big enough force feedback I received from the slave side. And the magnitude of time delay was actually not a problem. So based on this control architecture, we were able to manage over 2 seconds or even communication blackout. Okay. So since the video clip is quite long, so I will skip this. And why this approach is better than other control approach? There is other control approach like wave variable control approach to overcome communication time delay. But when we compared time domain passivity control architecture with wave variable control architecture, the time domain passivity control architecture actually minimally modify the original force, measured force from the slave side. If you compare this wave variable, actually wave variable approach may smash out the original control force a lot. Okay, so in that sense, TDPA show better transparency. And I transferred this control idea to DLL, and they have implemented this idea to their space Justin telerobotic system, as you can see here. So the guy who's controlling this is Jordi Artigas, who's my collaborator. So by implementing this idea and extending this idea to multi-door of redundant manipulator, he was able to see what robots see, and he was able to feel what robots feel. So he basically can do most of the tasks that the astronaut in International Space Station need to do. So this robot system is actually communicate through satellite, and there is 500 millisecond time delay. So I will skip this also fast. So you can do drilling job and switch operation and so on and so forth. Okay. And recently, we actually opposite the teleoperation. So astronaut in International Space Station control the Justin robot in the ground for demonstrating handshaking. So in one of the exhibition, they demonstrate handshaking performance with one of the politician in Germany. And we got great feedback from astronaut. And he said the feeling was great and quite transparent. And not only haptic and telerobotic system, we extended this idea to explicit force control. So there are two types of force control method in general: indirect force control, which does not use force sensor, and direct force control, which use force sensor. And in direct force control, there are also two types of direct force control: with inner loop position control and without inner loop position control. And we call direct force control without inner loop position control as a explicit force control. And the benefit of explicit force control is it provides precise force interaction, and it also provides high bandwidth force control. So it's quite interesting control architecture, but it's quite challenging to stabilize this due to sensor and actuator non-collocation problem. And together with researcher student at Stanford and DLR, we have extended this TDPA, time domain passivity control idea, to explicit force control of KUKA robot. So as you can see on the left, without TDPA, with simple disturbance, it easily goes unstable. And when the surface stiffness suddenly change, then robot cannot maintain explicit force control. With TDPA, we were able to manage stable force control, and even sudden force stiffness change doesn't actually destabilize the system. And we also extend this idea to teleoperation, including explicit force control architecture. So due to the high precision force control and high precision position control performance, we were able to conduct chip insertion task with communication time delay and through teleoperation with even sub-millimeter tolerance chip insertion task. So that actually shows quite a possibility and feasibility of teleoperation for dexterous manipulation. All right, so time domain passivity control approach actually shows good performance in haptic teleoperation and explicit force control even, but there is certainly limitation. With such a lightweight, small haptic device, 100 Hertz low sampling rate and 1 kilonewton per meter is already high enough to destabilize the interaction. Time domain passivity approach can stabilize this up to twice as stiff as stiffness, but as you can see, there is some red line, noise-like a behavior. Due to the on-off nature of time domain passivity control approach, actually, if we increase the stiffness certain level, then time domain passivity cannot stabilize this anymore. So we start to analyze what's the main reason, real reason of unstable behavior. Let's say this is the virtual environment, and this is the haptic interaction point. So you press in. Then if you look at the position force graph, this is the input and pressing path. And the area below this pressing path is the input energy you give to the system. And when you release, it follows the blue line, staircase blue line. And the area below this releasing path is the output energy from the system. So whatever small P gain you use, there is always bigger output energy than input energy. So system is always active. Then how come system doesn't diverge? Because passivity is simply sufficient condition. So that much amount of energy produced from the system can be dissipated by the intrinsic system damping. Then system is still stable. But if you increase the stiffness and controller gain, then the amount of energy get increased. So system cannot handle this anymore. Then system goes unstable. What we proposed is really simple. We save pressing path to the memory. And when we released, we bound releasing path with pressing path. That way, we can make system exactly passive. No more, active energy output. So by applying this, we were able to stabilize the interaction, and you can see there is almost no noise behavior, very smooth. And you may wonder how to extend this idea to multi-door case, but we have done this. So without memory-based approach, unstable. With memory-based approach, it was quite stable, and we were able to feel high stiffness interaction. And when we compare the performance with outdoor approach, that's even more interesting. So the dotted line here is without any control. So the maximum stiffness that small device can handle is 1 kilonewton, around 1 kilonewton per meter. But time domain passivity approach can enlarge this stiffness to up to 6, so 6 times. But memory-based approach actually can increase this stiffness to 290, so extremely high. So what does that mean, 290? It actually means 1 pulse of encoder change reach maximum motor current. Now, up to that level, the memory-based approach can stabilize the system. So that's the ultimate stiffness and ultimate controller gain, I guess. But if we want to implement memory-based approach, we need kind of special hardware, which is not actually special nowadays. We need FPG as a motor driver. But there are many people who don't want to modify their hardware, but still want to increase their stiffness. So for them, we propose another control architecture, successive force augment approach. So let's say there's haptic interaction point and virtual environment here. If you penetrate in, this is the perceived stiffness that you feel, force divided penetration depth. But while the haptic interaction point is inside of virtual wall, you suddenly shift up the initial the virtual wall position. Then the perceived stiffness suddenly increase, which is greater than the original stiffness. This looks like a trick, but actually it works when you implement this to haptic interaction, which is basically the same as introducing state-independent feed-forward force. So one penetration in and out, introduce force offset, and jump to the next lower level stiffness, and in and out, and jump to next, in and out, jump to next, and eventually you will reach to the higher stiffness, high force value. That idea has been implemented to Phantom, and we were able to achieve 5 to 7 kilonewton per meter for wall stiffness, which is extremely high, for Phantom. And there is, another idea which is similar but a little different. So pressing path, we took slow stiffness, low enough to stabilize, and releasing path is even slower than this. So it end up, still inside of virtual wall and in the middle of somewhere. It just looks like introducing offset. And after that, took another pressing path and releasing path, pressing path, releasing path, and eventually you will reach the desired force and stiffness profile while maintaining low stiffness. So while maintaining stable interaction. So that's kind of trick, but actually it works quite well. And we have implemented this idea to not only haptic interface, but also series elastic actuator control. Series elastic actuator is actually good for stable interaction, but due to the non-collocated nature of sensor and actuator, it's quite challenging to increase the controller gain. So if you use low controller gain, stable, but slow performance, slow response. When you increase the controller gain, it actually easily goes unstable like this. You may think by putting a damping gain, you can stabilize this, but not really. damping gain cannot stabilize this one, even more unstable. So we have implemented time domain passivity approach for this, and we can stabilize, but response become quite slow because TDPA sacrifice a lot of energy, have to kill a lot of active energy. And SSI, successive stiffness increment approach, we were able to make it move fast and also stable. So that's quite, shows good performance. And with twice faster reference trajectory, no impedance controller goes crazy, but SSI, TDPA, stable and still move quite a good performance, show quite a good performance, as you can see. And what happens if you drop down on our object, so give some impact. Then normal TDPA, normal impedance control, cannot manage this sudden contact, but SSI, TDPA were able to manage this. All right. Can I have a few more minutes? Is it possible? Yeah, yes, it's already 30 minutes. Okay.
That's okay. You have at least 5 more minutes, so don't worry about this.
All right. Okay. Good. Thank you. All right. Let's move on to admittance type haptic interface. So far, talking about impedance and some sorry, general robot manipulator control. So let's talk about admittance type. Admittance type works a little different way. So if you push the master device or robot, then we measure interaction force with force and torque sensor. And this force signal applied to admittance model, and admittance model provide a desired velocity or position to a robot controller, and robot controller control position and velocity. And this is the typical admittance model. And as you can see, you cannot actually lower down the mass below certain value. Because if you lower down the mass and inertia, then the sensor noise is actually magnified, so which influence to the position controller and desired position and velocity. So there is a certain limitation to lower down mass, just like there is a limitation to increase stiffness in impedance type. So for this simple admittance type haptic interface, 0.1 kilogram, we can render stable manner, but operator feel very heavy and sluggish. If you lower down the inertia to 0.01, then it feels lighter, but system already become unstable. So look at this oscillation. And lower down one more digit, 0.01, the system even more unstable, like this. You may think, you can stabilize this by strongly grasping, you can stabilize it. But no, it's opposite. If you increase your arm stiffness, the admittance type even goes more unstable. Okay. So we have extended time domain passivity control idea for admittance type haptic interface. So 0.01, which was unstable in previous case, it was stabilized. We were able to stabilize the interaction. And even one more digit lower, 0.001. Now it feels very light and stable. Like this. And by grasping, strongly, human arm stiffness, even though human arm stiffness increased, the operator can still match stable interaction. So which is good. Seems like good enough, but we want to lower down this value even further, and we want to have less conservative controller. So one of my former PhD student proposed another control criteria and control architecture, which is input to state stable approach. And in a sense that passivity criteria actually bound the produced energy by the initial energy storage, like this. The maximum energy output is bounded by the initial energy storage. But ISS, input to state stability criteria, actually bound simply random constant value. So as long as you can find random constant value found produced energy, then system is ISS stable and stable. So which can produce more energy, which means the control approach is less conservative. So we extended this idea and implemented this to same admittance type haptic interface. So you can see it's one more digit down, 0.0001, so 0.1 gram. So extremely light and even less damping, even smaller damping. So it feels very light and strong grasping doesn't influence stability. So we got very, very, good performance with ISS approach. So if we compare the range of the damping and inertia that admittance type can cover, ISS approach actually can cover a larger area than TDPA. The upper region is the range that each control approach can render in a stable manner. Right, so in summary, I have introduced several stable interaction methods: time domain passivity, memory-based passivity, successive force augment, successive stiffness increment, input to state is stable, a lot of control approach. So I hope you guys can have some, brief idea about each control approach. And if you have some system, your own system, depends on application, maybe you guys can selectively use those control approach for your own application. And I recently opened my lab, so there are open master, PhD, and postdoc position in my new lab at KAIST. So if you guys are interested in, and please don't hesitate to contact me. All right, thank you.
Thank you very much, Professor Yu, for your wonderful talk. So we had some questions from chat. Meanwhile, while we are preparing, so I just wanted to maybe for you to elaborate for the more general audience. So you've talked about many research applications about increasing stiffness, for example, for haptic interfaces. Can you give us any examples of some exciting applications of haptics in teleoperation? Maybe the most interesting applications for you in real life industry or any other applications of this technology apart from research?
Okay, so I believe haptic and telerobotic system has long history, more than 60 years, and one of the typical application of haptic and telerobotic system is sending a robot to digester in a hazardous environment instead of human. So like underwater exploration and nuclear plant, nuclear toxic waste handling, and also maybe nowadays it will be very interesting to deal with COVID-19 situation, because human don't want to, doctor and nurse don't want to meet the patient. So that kind of application is also very interesting application for COVID-19 situation as well. So typical application is digester and dangerous environment, but nowadays this hospital and COVID-19, dealing with COVID-19 situation and meeting a patient with highly dangerous situation, that's also a good application for haptic and teleoperation, I guess.
Thank you very much. And I believe we had the audience, Sergey Kalibin, who wants to ask the question by audio. Sergey, please go ahead.
Yeah, Igor, thank you very much. Professors, thank you very much for the wonderful talk. I have a question related to the theory, more like that. So in a number of tasks that you mentioned, there are approaches, PBC approaches, and one of quite well known is related to using energy tanks, also for teleoperation and for manipulation and so on. Can you highlight the difference between the approach that you describe and you present and the energy tanks concept? Thank you.
Okay, I see. That's a very interesting question. So basically same energy tank, basically same. So after I proposed this concept, one research group in Italy, and they also propose another type of approach, which is energy tank, which is pretty much the same, but there's one big difference. Energy tank try to use some already dissipated energy, reuse already dissipated energy, but in time domain passivity approach, we actually do not use already dissipated energy. So in some sense, you may some researchers think energy tank is less conservative, but how much energy you can reuse from the dissipated amount of value, that's actually a very critical factor to stabilize the system. But time domain passivity do not use already dissipated energy because it's already gone.
Okay, can I ask a bit further? So in your case, in most of the scenarios what you illustrated, you used, let's say, as effort and flow mechanical variables like speed and force, right? Is it possible to use as effort and flow like electrical variables, or different sets of variables to do the same?
That's a really wonderful question. Yes, that's possible. So basically energy is same. So you can use voltage, current, and you can use other variable to measure energy. So that's possible, but actually I haven't done this yet, and that's one of the topic that I really want to do. But you can actually measure voltage and current, but that's not that straightforward. If you make it passive, that was not straightforward. So I didn't actually do that, but that's definitely a very interesting direction.
Yeah. Because it looks like the critical element for all the examples is the FT sensor, which are not always available and quite expensive, I would say.
Oh, okay, I see. But we do not use FT sensor in that sense because the way I implement it, velocity is the actual velocity you can measure from encoder or the differentiated value from the encoder, and the force value is commanded force or current. Or you can multiply current to current constant. That's the force value that I have used, not the actual force sensor information.
Okay, yeah. Thank you for the answer. Yeah. Thank you.
Okay.
Thank you very much, Professor Yu. There were just maybe one last question in the chat. So when you discussed PC algorithm, right? So what should be the initial values for alpha coefficients? If you can elaborate maybe any general remarks.
The ISS, input to status stable.
Yes, I think so.
Oh, okay. There is no initial value. There is no initial value. So the key concept of ISS approach, basically time domain ISS approach, is that we don't need to specify this alpha value by using some of the approach that I cannot explain right now. I didn't actually prepare that slide here. Then automatically we can find some random alpha value which is constant. So we don't need to specify constant alpha or initial alpha.
Okay, thank you. And unfortunately, I think we're out of time. So I would like to thank you, Professor Yu, once again for coming and delivering your speech. And I'll be looking forward to having you in the future editions of the conference. Thank you very much.
All right. Thank you. Thank you so much.